Before we jump into writing proofs or learning how to write proofs, we need to practice converting given statements into universal conditional statements. Because we're going to lean into this idea of a universal conditional statement and how we can turn it into a universal modus ponens or a universal modus tollens in terms of writing proofs. So let's go through several examples here. So let's start first with A. A says, prove that the sum of any two even integers is even. So the statement that we're going to need to translate is this one that says the sum of any two even integers is even. So if we want to translate this statement into a universal conditional, we can say, all right, well, sum of any. Any means any, all, right? This all leads to a universal quantifier. So we're on the right track. So for all, well, we can't really say even integers because then we won't have an if and a then. So let's just start with integers and let's call them m and n. So for all m and n in the set of integers, if both m and n are even, then their sum, so the sum we could just write as m plus n, is also even. So we would say for all m and n in the set of integers, if m and n are even, then m plus n is even. So we can take this idea and we can extend it into part B. Prove the sum of any two odd integers is even. I believe I might have given you this one on the exam. So again, what we're trying to prove is here, the sum of any two odd integers is even, so that's the statement we want to convert to a universal conditional. So again, we've got two integers, so I'm going to call mine m and n, and they're both integers, and we're going to say if m and n are odd, then their sum, m plus n, is even. So what happens if we want to say, we want to prove that the sum of two consecutive integers is odd? So we have to first define, once we know that we're trying to rewrite that the sum of two consecutive integers is odd, we need to define what it means to be consecutive. Consecutive means one after another, right? In order, right? Sequential, that might be another nice way to put it. Consecutive means if I say 5, the next consecutive integer would be 6. If I say 17, the next consecutive integer is 18. So based on this idea, we want to prove that the sum of two consecutive integers is odd. So there are a couple of ways we can write this one. So we could say for all m and n in a set of Z, if m and n are consecutive, I think I spelled it wrong, give me a second there, is consecutive, right? Then m plus n is odd. Or we might say for all m and n in a set of integers, if m equals n plus 1 or n equals m plus 1, then m plus n is odd. The second one is very oddly specific, probably, for you at this point. But what it's saying is two consecutive integers. We don't know which one comes first, whether it's m or it's n. So if either m equals n plus 1 or n equals m plus 1, meaning I either have 3, 4, or I have 4, 5, however we want to say it, then we would say their sum is odd. So this will take us through sections 4.1 and 4.2. Those are actual statements, some of which we're going to prove. So let's see what happens when we start moving into 4.3, where we start talking about rational numbers. And remember, the symbol for rational number is a Q, not an R. Remember, R is for real numbers and the Q is for rationals. So let's prove here every integer is a rational number. So this is one of the times where things get a little more challenging in order to figure out your domain. Because if we said for every integer, which I guess we'll call this one just n since we only have one. So let's say for every n in a set of integers, if n is, a rational number? Nope. N is an integer. Well, that would just say if n is in z, then n is a rational number, which means n is in q. But then our domain is redundant with our hypothesis. So there's a better way to do this. So instead of having our domain match our hypothesis, we're going to change this. And remember how we talked about integers were special cases of real numbers, right? So we're going to change it to say, for all n in a set of real numbers, if n is an integer, then n is rational. So we're not going to do the blue one, and yes, we're going to do the red one. And again, this is simply because our domain and our hypothesis of our conditional statement would be identical if we didn't. So sometimes you find out that when you write your conditional statement, you sort of have to back up and go back to your domain and broaden it a bit. So we're going to see this happening in the next two problems as well, because the next one says prove that the sum of any two irrational numbers, the sum of any two rational numbers is a rational number. So here again, it's because we're trying to bring into the conversation the type of number we're talking about, to which set it belongs, whether it's a real number or an integer or a rational number. And so that's where things get a little bit tricky, because we end up saying, okay, so let's put our two rational numbers, now m and n, into our set of real numbers again, because now our if is going to say is if m and n are both in the set of rational numbers. So if m and n are both in Q, then their sum, m plus n, is also in a set of rational numbers. You'll find these weird statements where we have to dial the domain back to real numbers only happens in very specific kinds of problems. It's not all of our problems. So let's try another one. F says prove that the product of any two rational numbers is a rational number. So here we're trying to show the product of any two rational numbers is a rational number as universal conditional. So again, we've got two rational numbers. So let's say for all m and n in the set of real numbers, if m and n are rational, then their product means multiplication, m times n, then is rational. G is a little different. It says prove that for all integers m and n, if m mod 5 equals 2 and n mod 5 equals 1, then mn mod 5 equals 2. So this one, it's kind of written out already how it is that we're going to put this in a universal conditional. Because we were saying for all integers m and n, well, that's our domain. If this, then that. Sounds pretty straightforward to me, so we'll take it. For all integers m and n, Okay, so m and n are both in the set of integers. Okay, if m mod 5 equals 2 and n mod 5 equals 1, then mn mod 5 equals 2. And it doesn't matter at this point if you understand what a mod is or not. We're going to learn that when we get to section 4.4 or 4. No, I think that's 4.5. We're going to learn about what div and mod mean. So please don't worry if you don't know what mod is just yet. For our last 3 examples, let's see what we have. We won't know all of this terminology just yet, but that's okay. Any 2 consecutive integers have opposite parity. So this is going to be one of those ones where, again, we can employ the idea of consecutive or we don't. So let's try it without the definition of consecutive. So for m and n in the set of integers, if m and n are consecutive, right, then they have opposite parity. Or we'll say then m and n have opposite parity. So we're going to learn when we get into sections 4.1 and 4.2 what parity means. Parity means whether it's even or odd. It's analogous to having a sign. What's the sign of our number? Well, is it plus or minus? That's really what we're looking for there. And I mean sign like S-I-G-N, not sign as in S-I-N-E from trig. But if we dig into this idea of what consecutive is, we could say for all m and n in a set of integers, if m equals n plus 1 or n equals m plus 1, right, same thing as before, then m and n have opposite parity. So what they're saying here, or what we're trying to say, is that if you have 2 consecutive integers, 3, 4, 17, 18, 27,000, 27,001, whatever it is, whatever set of 2 integers we have, if they're consecutive, one is even and one is odd. That's what we're saying here. How about, let's see here, for any integer n, n squared minus 5n plus 75 is odd. So here, because we're talking about n being an integer, we're going to have, if we're going to leave, so for all n, if we started doing it off with n being an integer, then we would say if n is an integer, then n squared minus 5n plus 75 is odd. So we're going to dial back our domain a little bit bigger, zoom out a bit to the real numbers. So for all real n, if n is an integer, then n squared minus 5n plus 75 is odd. And then for the last one, it says for any integer m, m squared plus 4n plus 8 is even. So for this one, we're going to have for all m, right? So for all m in a set of real numbers, if m is an integer, then m squared plus 4m plus 8 is even. Oops, I just saw a typo. This should be m. So this should be a really good, quick reminder on how to convert from a given statement, particularly one that might be more implicit, to a universal conditional that's going to lay the basis for what we need to do in chapter 4.